Suppose that this is the transaction of the Alice. This is the recipient address. This is the sender address. This is the signature. How Alice calculates the signature? Using here, I have a function that at first creates the hash of these fields: recipient, address, amount. It is recipient. And nouns. Then here, using this using this command, suppose that this is the recipient address. I have copied it from here. This is the transaction. Okay, this is the transaction that Alice wants to send to Bob. In fact, Alice wants to propagate these transactions through the peer-to-peer network. As you can see here, this is the recipient hash. So Alice calculates signature hash using recipient hash. Amount is 10. Suppose that the fee is 1 and the nouns is 1. And D is the hash of this data. Now using this command, Alice's private key, alice.sign, Alice creates this signature. So SIG is the digital signature of this data. And this is the output, okay? And now I have it here. I have copied it here. Now, Alice sends these transactions through its neighbors, its peers, okay? Every peer, simply using Alice's public key, this is Alice's public key, can verify that everything is okay or not. There is no error, so everything is okay. But what if Eve changed something? For example, if Eve changed this address, suppose that this is Eve address. I just changed one address. Now we have a different address, and suppose that this is the Eve address. Other nodes will check, but at first, other nodes again calculates D. And now, when they receive this transaction, they have this address. So they must change. So they must change this address again. And now, if they verify, they see invalid signature, okay? And this is how others will be prevented from tampering the transaction. You see? This is one of the parts of transaction verification. So, suppose that we have a transaction. Each transaction must have this information: recipient address, amount, fee, nouns, amount, fee, nouns, signature, and finally transaction ID. What? Please note, each person who wants to create a transaction creates something like this. And send this through the network to its neighbors. Okay? So others using this signature simply can check that everything is okay. If someone changed the amount, if someone changed the recipient address, checking the signature, everything, checking the signature, every changes, every tampering will be shown. There is another thing here. Every transaction must have a unique identifier. Every transaction must have a unique identifier. What is transaction ID? Transaction identifier or transaction ID is simply calculated using the hash of all the fields in a transaction, calculating the hash of recipient address, sender address, amount, fee, nouns, and the signature. Okay? See here? This is a function, calculate transaction ID. Sender address, all the fields, recipient address, sender public key, amount, fee, nouns, signature. Then here using these commands, add them to the hash. Digest update, sender hash, recipient hash, put everything beside together and generate the hash. So here I can generate a transaction ID. Transaction ID is equal to, let me call this function. Sender hash. This is our transaction sender hash. This is the sender hash. But I must convert it using this command, bytes from hex. Okay. So this is the recipient hash. And now sender hash, I must cut this part and replace it with this part. This is the sender address. Okay, I put it here. Sender public key. We have the sender public key here. Sender public key. This is the sender public key. Okay. This is the sender public key. Amount is 10, fee is 1, nouns is 1, and signature again bytes from hex. But I copied this signature. This is the signature. Bytes dot from hex. Okay. Oops. I just have to sender public key. Data must be byte. Okay. This public key must be converted to a byte object. However, it's not important. Transaction ID is calculated using such a command, okay, using such a function. This is the transaction ID, and it's a unique value for every transaction. So using this ID, you can trace for everybody how much money he has or she has, okay? But let's talk about nonce. What is nonce? What is nonce? In my example, I considered 1 for nonce. Nonce is a number which is used once. Suppose Bob wants to send 10 Bitcoin to Alice. Okay? If we don't have the nonce, so in our transaction we have Bob address, we have Alice address, we have 10, we have 1, we have the signature. Okay? What is financial fee? Nonce? Nonce is not financial fee. No. Fee. This is fee. Fee is the cost of putting the transaction inside the block. Okay. Suppose Bob wants to send 10 Bitcoin to Alice. Okay. So Bob must create a transaction like this. Bob and the ID. Transaction ID here. Bob address, Alice address, the amount is 10. Fee is 1, signature ID. Okay? Now, suppose that tomorrow, again, Bob wants to send another 10 Bitcoin to Alice 2 times. Okay? Suppose that, again, tomorrow, Bob wants to send another 10 Bitcoin to Alice. So he must create another transaction. The transaction will be exactly the same as the previous. So other nodes in the network says, oh, you have previously created the transaction, and before miners put the transaction inside the block, and they will reject the new transaction. Understand? This new transaction is exactly as the same as the before. So only so all the intermediate node and the miners will reject the new transaction because they check that and see that previously they have processed such a transaction. Everything is the same. Bob address, Alice address, the amount, the fee, signature, and ID. Please note, ID is the hash of these fields. So everything is the same. So nonce is a number that in each transaction is used only once. So for this transaction, nonce is 1. But for tomorrow transactions, it will be 2. For another transaction, it will be 3. Every transaction which Bob creates will increase the nonce by 1. For the first transaction, it's 1. For the second one, it's 2. For the third time, it's 3. For the fourth, is 4. Okay? So nonce causes that the signature and the ID be a different, so it's a different transaction. So all the nodes, all the miners in the network understand that it's something different. And this is the transaction verification. Nobody can tamper the transaction. And also another question, and I expect you answer me. Suppose that Bob creates a transaction, okay? Suppose that Bob creates a transaction and sends 10 Bitcoin to Alice, creates the transactions, sent it through the network, and that's it, finished. How the network, this is the question. Let me write. Tell me how the network prevents Bob to deny sending that 10 to Alice. Tell me how the network prevents Bob to deny sending that 10 to Alice. It's important. It's an important question. Here, Bob creates this transaction, sent it through the network. Okay? Maybe Bob wants to cheat, and tomorrow says, oh, that's not me. That was someone else. How other nodes in the network understand that Bob is cheating? See the information inside the transactions, and according to this information inside the transaction, answer me. Which field of this information prevents Bob from cheating? Who can answer? Nobody? Exactly. That digital signature prevents Bob from cheating. Remember, how digital signature is created? Private key dot sign. Okay? Who has the private key? Only one person, Bob. If we have this signature here, it means that this signature was created using Bob private key. And who has the private key of Bob? The only person is Bob. So this digital signature inside the transaction prevents Bob from cheating, prevents Bob from denying sending the money. Understand? So this digital signature plays an important role inside the cryptocurrencies. In fact, this signature prevents others to tamper the transaction. Also, this signature prevents the sender to deny sending the money, and it's very important. So this digital signature plays an important role, and that's it. An important role inside the cryptocurrencies. In fact, this signature prevents others to tamper the transaction. Also, this signature prevents the sender to deny sending the money, and it's very important. So this digital signature plays an important role, and that's it. And so let me show you another thing. This is the slides. This is the slides about verification. As you can see, I explained it today, but I explained it through the Python code because I want you to better understand the problem. But let's check the slides. Identity problem. How do we know that Alice initiated the transaction? Using its signature, okay? Identity problem. How do we stop Alice from later denying she sent the money? Again, from the signature. This is the answer. Alice signs the whole transaction using a digital signature, as I showed you, okay? Right address problem. How do we know that Bob received the transaction? It's a simple question, because the address, it goes the hash of his public key. Again, I showed you. Every address is the hash of the public key of persons, okay? So since we have the address of the recipient, so we are sure that Bob or the recipient will receive the transaction. Money availability. How do we know that Alice has the money? Okay, it depends on the cryptocurrency. In a cryptocurrency like Bitcoin, the network keeps track every unspent transaction for every address. So since the network keeps track the unspent transactions, so the network now everybody has how much money. In another cryptocurrency like Ethereum, every address associated with a balance like real banks, okay? So simply checking the balance of the, for example, Alice, every node can check that Alice has enough money or not. Another question, how do we know that no money is being created by the transaction? Digital signature prevents tampering the information, but double spending must be answered later when we want to discuss the blocks and mining, okay? So we can answer this question now. Later we will answer it. And this is digital signature. All these questions answered using digital signature. How? In fact, the identity problem is solved by digital signatures. Remember, Alice has a public key, PK, and a secret key, a private key, SK, okay? Two functions, signature, verify. I showed you these two functions inside the Python code. Signature signs a transaction using the private key. This is the private key, okay? And returns the signature, a string, okay? As I showed you in the code. And another function called verify. Verify takes public key, a transaction, and a string. That string is the signature which creates using this function, okay? So str, this str here, this str is the output of this function, okay? And checks if this transaction signature is the same as this str, so it will be return, this function return true, otherwise it will show an error as you saw in the Python code. Okay, so using these two useful functions, everybody can check and can verify the transaction. So many problems of tampering the transaction, denying the transaction are solved using digital signature. About Bob, if Bob wants to spend the money, if Bob wants to really receive the money, must prove that he has the key. How he can prove that? Since Bob has the secret key, the private key associated with the public key, so simply he can prove that he is the owner of the money. What are the conditions that make Bob the only recipient? It's a good question. Let me answer this question. I write your answer here. Bob has everybody like Bob. I'm talking, you ask about Bob, so I'm trying to answer with Bob, okay? Bob, like everybody, has a private key. It's a secret key, okay? I'm trying to answer you, Nuradan. Bob has a private key. Since he has a private key, he has an associated public key. Okay? And what is the recipient? Recipient address is the hash of that public key. And as you can see, these hash functions generates a unique address. So since Bob has a private key which generates the public key, the only person who can spend the money, who can receive the money, is Bob. Because the only person who can generate this information is Bob, because Bob only has this private key. Understand? If you want to spend this money, you must prove that you are the owner. How you can prove that you are the owner? Your answer is in the next slide. Let me to topic 4, lecture 1, topic 4, and this is your answer. In fact, Alice says lock, when Alice sends the money to Bob, locks the output using this. There's a PK script here, okay? In the slides, there is enough information about what is PK script or SIG script, okay? This is PK script. Alice locked the output with this. The person who wants to spend this money must unlock this code. This is an stack-based code, okay? The only person who can unlock this is Bob, because Bob has the private key associated with the public key here. Okay, this is about the output, this is the Bob input. Okay, and here is trying to answer your question. There is a stack. In the stack, Bob's signature. At the bottom of the stack, we have the Bob signature, then we have the Bob's public key. This is the P script which Alice locked the output. Okay, OP-dupe means duplicate the element on top of the stack. So that was the initial state of the stack. After running the code, we have another public key here. The second instruction is OP hash. This is the address. This is what you are asking. This is the address of Bob. This is the recipient address. This is the Bob address. So we have this here. Then intended address, it will be pushed to the address. This is the address that Alice showed it in the transaction. Equal verify, check that these two addresses must be the same. So here Bob is trying to prove that this is the right address, and finally check the signature, checks that the signature is true, and that's it. Another question you asked that is there a commission in both Bitcoin and Ethereum? Yeah, every cryptocurrency has a commission. Okay, in fee, the commission is called fee. The commission is called fee. No, you are asking, will the commission in Ethereum increase with the increase in the transferred amount? Please note, in Ethereum, the fee is increased with the size of the transaction, not only with the amount. For example, suppose that the size of a transaction is, for example, 100 byte. For example, another, suppose that is 200 bytes. Certainly, the fee associated with this transaction is greater than this one. Okay. So larger amounts may be causes to larger transactions, but not necessarily, because, for example, if our amount is 15 Ether, okay, and another is 30 Ethereum, both have the same size. Okay. In fact, this commission is calculated according to the size of the transaction. Okay, the bigger transactions must pay more fee. Okay, and that was about the transaction verification. The most important questions was that how the network prevents others to tamper the transactions, how the network prevents the sender to deny the transaction, and how the recipient can claim his or her money. And these was 3 main questions that must be answered, and I tried to answer these questions. I tried to explain these concepts using Python codes. Now, if you have any question, please let me know. Otherwise, see you later. No more question? Those Python codes, previously I sent those Python codes, and previously in the previous sessions I explained those parts: how to generate private keys, how to generate public keys, how to sign some information, how to verify some signed information. So watching the previous videos, I'm